When network defenders detect an active breach, their first response is to sever the connection. They block the IP, isolate the host, and assume the threat is neutralized. But sophisticated attackers anticipate this response, building an invisible line back into the network before the primary connection is ever cut. Gaining initial root access to a server is rarely a permanent victory. In practice, an active exploit is a fragile, noisy, and precarious state for an attacker. The act of exploiting a vulnerability generates anomalous processes and error logs. These behaviors immediately alert the network's SIEM systems. SIEM stands for Security Information and Event Management, a centralized platform that analyzes logging data across a network to flag suspicious activity. Once an alert triggers, the attacker's window closes. A security operations center analyst can sever the attacker's shell session by rebooting the server or killing the compromised process. Therefore, the immediate post-exploitation objective is survival. The attacker must transition from a loud, active attack to a state of invisible, cryptographic persistence. Standard incident response assumes that patching the software flaw and resetting administrative passwords evicts the attacker. This logic fails against a prepared adversary. Persistence relies on cryptographic keys rather than passwords. By planting a key, an attacker creates an authentication mechanism that renders administrative password resets ineffective. This method exploits the core mechanics of asymmetric cryptography, a system that utilizes a mathematically linked pair of keys, one private and one public. The attacker uses OpenSSL to generate an RSA encryption key pair. The OpenSSL genPK command creates the master private key, kept strictly offline as cryptographic proof. A subsequent command extracts the public key string, acting as a lock implanted on the target server. The attacker takes this public key string and appends it directly into the target server's /root/ssh/authorized keys file. The secure shell, or SSH protocol, utilizes bidirectional authentication. When the attacker attempts to connect, the server checks its authorized keys file, sees the planted public key, and issues a cryptographic challenge that only the attacker's private key can solve. This specific public key authentication entirely bypasses the target's PAM stack. PAM stands for Pluggable Authentication Modules, the framework that enforces password policies and prompts users for credentials on Linux systems. Because the SSH protocol verifies the cryptographic signature before PAM ever requests the password, the compromised server accepts the connection silently. Administrators can rotate every password in the network, and the attacker will still log in directly as root. With Common Access secured, the attacker extracts the material required to move across the internal network. To move laterally, the attacker needs legitimate credentials. Linux systems split credential storage into two components. The first is the /etc/password file, which maps user accounts, user IDs, and directory paths. The actual authentication data lives in the highly restricted /etc/shadow file. This document contains the salted password hashes, the mathematically scrambled representations of the user's actual plaintext passwords. Using their persistent root access, the attacker executes standard copy commands to duplicate both the password and shadow files into temporary text documents. Strict operational security dictates that an attacker must never attempt to crack these password hashes directly on the compromised target machine. Cracking hashes requires symmetrical brute forcing, a process that attempts millions of mathematical combinations. Running this on the target causes massive, sustained CPU spikes. These sudden compute spikes trigger behavioral heuristics in modern EDR agents. EDR stands for Endpoint Detection and Response, a security software installed on host machines that monitors system activity for anomalies. To maintain their undetected status, the attacker exfiltrates the encrypted hashes over their secure tunnel to their own hardware. All computational lifting happens off-site. On their local machine, the attacker begins the data preparation phase using a utility called unshadow. The unshadow command merges the exfiltrated password and shadow files. It aligns the user mapping data with the corresponding encrypted hashes, creating a single file ready for decryption. Hashcat, a password recovery utility, leverages a high-performance GPU array to process encryption algorithms in parallel. The attacker executes Hashcat against the merged file, applying the M1800 flag. This targets the SHA-512 cryptographic hash algorithm, the default standard in modern Linux distributions. Applying a dictionary attack, The attacker feeds massive word lists into the GPU array, testing millions of combinations per second against the stolen hashes. By uncovering instances of weak passwords and widespread reuse on their own hardware, the attacker secures valid, plain-text credentials. They can now authenticate as legitimate users throughout the network without triggering login failure alarms. Armed with valid credentials, the attacker weaponizes their persistently compromised edge server, turning it into a routing bridge for deeper network penetration. This edge server is dual-homed. It has a public-facing IP address touching the internet and an internal network interface connected to a protected VLAN. A VLAN is a virtual local area network, which logically separates devices into isolated subnetworks. To exploit this dual-homed status, the attacker deploys a tool called SSH Shuttle. SSH Shuttle operates by creating a transparent proxy server layered directly over the already established encrypted SSH backdoor tunnel. This proxy acts as a virtual router. It takes all of the attacker's local reconnaissance traffic, funnels it through the encrypted tunnel to the edge server, and routes it into the internal VLAN. By establishing this routing bridge, the attacker moves past the perimeter. Their traffic originates from a trusted internal server, allowing them to operate from inside the organization's own network. The attacker now begins network reconnaissance, scanning the internal environment through their newly established transparent proxy. They execute an nmap command from their external machine, targeting internal subnet ranges to discover new targets for their stolen credentials. However, routing scans through a proxy introduces a technical constraint. Nmap's default, stealthy SYN scan, designated by the -SS flag, will fail. A SYN scan requires raw packet crafting at the operating system level. It is a probe that sends a synchronized packet to a target port, but intentionally drops the connection before a full handshake can complete. SSH proxies cannot forward these raw, low-level packets. To map the internal network, the attacker must force Nmap to use a TCP connect scan instead, using the -ST flag. The -ST scan utilizes standard operating system calls to complete the full three-way TCP handshake. Because it creates a legitimate, fully formed connection, the proxy can successfully route the traffic to the internal targets. This progression, from cryptographic persistence to internal proxy routing, demonstrates why perimeter security is insufficient. Once an adversary establishes a foothold, the attacker's presence becomes indistinguishable from legitimate internal traffic.